Welcome to Learner's Corner, and today we shall be dealing with elasticity in physics. So the topic today is elasticity. So elasticity is simply defined as the ability of a body or a material to regain its shape and size after distortion. So if a body, for example rubber band, when you stretch it or when you compress it, it will regain its shape. Because of that ability of regaining shape, we see that rubber band is elastic. So that process is called elasticity. So let me write it on the board. We have this is the ability of a body or material to regain its shape and size after distortion. And we will talk about elastic material. So an elastic material is a material that has that ability of regaining its shape and size after distortion. For example, I used rubber band as an example. So rubber band is an elastic material. So this is a material that regains its shape and size after distortion. So there's a law that governs elasticity, and the name of the law is Hooke's law. So we will be discussing Hooke's law right now. Hooke's law. Okay, so Hooke's law tries to explain to us what happens to an elastic material. So you have we define Young modulus as the ratio of tensile stress to tensile strain. Yes, Young modulus is defined as the ratio of tensile stress to tensile strain. Let me write it down. This is the ratio of tensile stress to tensile strain. So in order to write the formula, we'll be using Ym to represent Young modulus. So it's going to be equal to tensile stress divided by tensile strain. So this tensile stress and this tensile strain. So in order to ease understanding, we are going to also talk about what tensile stress is all about. So when we talk about tensile stress also is the ratio of force to area. Yes, the ratio of force to area is tensile stress. So tensile stress is the ratio to area. So, and the formula is going to be tensile stress equal to force as F all over A as area. And you know that the SI unit of force is Newton, while that of area is meter square. So we are going to be having the SI unit of tensile stress as Newton meter per square. So this is the SI unit of tensile stress. So we've explained what tensile stress is all about. Let's also explain what tensile strain is talking about. So tensile strain. So tensile strain is the ratio of extension to the original length of a material. The ratio of extension to the original material, and it's going to be a tensile strain equal to, we use E as extension all over length. So it's not going to have any SI unit because of extension is measured in meter, and length also is measured in meter. So meter will cancel meter, making tensile strain not to have an SI unit. So now you now know the formula. Okay, let me just put it this way: tensile strain. So now you now know the formula of tensile strain. You now know the one of tensile stress. So we'll be using this in order to get the formula of Young modulus. So note this, and also note this. So this is the formula of tensile strain, this is the formula of tensile stress. So right from the beginning we said that Young modulus is the ratio of tensile stress to tensile strain. So I say we'll be using Ym as Young modulus equals to tensile stress all over tensile strain. And we know that the formula for tensile strain, for tensile stress rather, is force all over area, and this division sign is going to give us, tensile strain will give us extension, which is E, all over length. So because of this division sign, we are going to have this as the final formula for Young modulus. So if you are asked to find Young modulus, you should check out for force, you should check out for length, also check out for area, and check out for extension, and be able to pull through. So this is the formula for finding Young modulus of a material. So this is the formula, and we are going to, in the course of this learning, also we will be doing some examples and also calculations. So we'll talk about, let's talk about work done in a spring or elastic spring. Okay, so we see that work is done in an elastic spring when a maximum force displaces an elastic spring from its original position, causing an extension. So that's it. Work is done in an elastic spring when a maximum force or an average force displaces an elastic spring from its original position, causing an extension. So we are going to have work done. We use WD to represent work done to be equal to average force times extension. So average force times extension. And we know that when we talk about average force, that we are going to have initial force and we are going to have the final force. So let's use F1 to be initial force plus F this to be final force divided by 2. Remember, we are taking the average. So this, the initial force already is going to give us 0. So we are going to be having 0 plus F over 2, which is going to give us, so 0 plus F is going to be F, and you know that there is a 1 before this F, there's a 1 before this F, so it's going to be 1 over 2 F. So 1 over 2 F. Let's remove this small F. Let's remove this small F. It's going to be half F. Remember, we talked about extension here. So bringing that extension down as E, we are going to have, look at it. So this average force times E, which is extension, will be giving us work done equal to half F E. So the formula for work done is half Fe. Yes, so I'm going to expand this formula, but just get it in mind that work done is half Fe. So we said work done, we've established the fact that work done in an elastic spring or spring is equals to half Fe. So from Hooke's law, we say that force is equal to Ke, right? So if force is equal to Ke, bringing it down to this place, we are going to have equating this. So we are going to have Ke, and remember we have another E that is here. So bringing the E here, we are going to have work done equals to half Ke squared. That is this E times this E is going to give us E squared. So this is work done equal to half Ke squared. So we'll be solving some examples from this elasticity as a topic. It's a very interesting topic. So let's solve some examples. So we'll be solving some examples here, and I'll read from a small paper which I have here 2 questions. So I'll solve the first one. It says a spring is stretched. A spring is stretched 40 millimeter by a force of 15 Newton. What is the work? What is the work done by the force. So here what we are going to do is we will first write down the parameters in which we were given. We were given extension to be 40 millimeter, and we also given force to be 15 Newton, and we are looking for WD, which is the work done. And from what we are given and what I have explained on work done, we know that work done is equals to half F E, which is equal to half times force, which is 15, times, we are going to change this 40 millimeter to, we are going to convert millimeter to meter. And in order to convert millimeter to meter, we do 40 divided by 1000. So 40 divided by 1000, that's what we are going to do here. So we are going to do 40 divided by 1000, which is going to give us 0.04. So we'll bring down 0.04. So we'll have 0.5, which is half, times 0.04 times 15 is going to give us 0.3 joules. So when you are solving, remember to put your SI unit. Work done is measured in joules. So